Over the course of these next couple files, these next few videos, we're going to be sort of combining chapters 5 and 6. Over the number of times I've taught this course, I find that it really works better if we sort of integrate these two chapters together. And so that's what we're going to do here. So in these two chapters, we're going to be dealing with the concepts, with starting to look at chemical reactions, and then a concept known as stoichiometry. So when we look at a chemical equation, what kind of information does the chemical equation give us? And then from that chemical equation, what can we use it for? So let's say we have the following equation. So here's a fairly basic chemical equation. On the left side of our equation, we have our reactants, or our starting materials. These are what we would be adding together if we were actually doing the reaction in the lab. And then you'll notice we have an arrow, and that goes over to the right side of the equation. The right side of our equation represents our products, or what's formed if the reactants that we put together were to react in the lab. Now, there's also some other information here. You'll notice that each one of these has a subscript by it. And in each case, it's a lowercase g. What that lowercase g tells us is that the substance we're working with in the reaction is a gas. So we can also often see in these types of situations, we'd see L, which would designate that the compound was a liquid, as well as S for solid. There's one more term that we might see, and we actually see it quite commonly, which is the term AQ. AQ stands for aqueous, and this means that the substance is dissolved in water. So in addition to telling us what the reactants are, in this case H2 and O2, or hydrogen gas and oxygen gas, telling us what the products are, water, as well as telling us the phase that we'll find them in, we also often find that we have numbers before our reagents. And for those numbers, in this case, we have a 2 in front of the hydrogen, but there's no number in front of the oxygen here. There's also a 2 in front of the water. Now, if there's no number in front of a compound, then we assume that it would be 1. Any number that's not 1 would have to be drawn in. So what this tells us is that we have the following going on. Two molecules of hydrogen gas react with one molecule of oxygen gas to form 2 molecules of water. There's only one problem with thinking about reactions in this way. Anyone know how many molecules are contained in a single drop of water? So, in a typical drop of water, we might have approximately 10 to the 20 water molecules. And so thinking about compounds in this way doesn't really help us in the long run. Or let's think about it in another way. Let's look at copper. So let's say we have one copper atom. The average mass of a copper atom is 63.546 AMUs. But the problem is AMUs are very, very small. So how many grams is this equivalent to? So see if you can calculate the number of grams that are the mass of one typical copper atom. All right, so to do that, hopefully you used the conversion factor for grams to AMUs. That's something we can look up. 1.66 times 10 to the minus 24 grams is equal to 1 AMU. And so if we calculate that, we get that the average mass of a copper atom is 1.05 times 10 to the minus 22nd grams. So it doesn't really make a lot of sense to talk about these things in terms of atoms or molecules because the quantities are so small. Or we would have to talk about such a large number of atoms that it's really not something that that really makes sense to us. So what we use instead is this concept of a mole. And a mole is equal to 6.02 times 10 to the 23rd of whatever the object is. And this number is known as Avogadro's number. So what happens now if we talk about 1 mole of something? So let's say we have 1 mole of copper atoms. Well, we just calculated the mass of 1 copper atom, which was 1.05 times 10 to the minus 22 grams. Now let's multiply that by Avogadro's number, 6.02 times 10 to the 23rd. So we're saying what would happen if we have 1 mole of copper atoms? So we calculate that out. We get 63.546 grams. Or in other words, 1 mole of copper is equal to the number of grams that we find on the periodic table. So is that true for anything? Well, let's look at our periodic table. here's our periodic table again. So now let's say we had 1 mole of carbon atoms. What would the mass be? Well, all we have to do is look at the periodic table, and we find the mass of carbon, 12.011. And so we now know that 1 mole of carbon atoms will have a mass of 12.011 grams. What's the mass of 1 mole of palladium atoms? Again, we look on the periodic table. The molar mass of palladium is 106.42. Therefore, 1 mole of palladium will weigh 106.42 grams. Now, this doesn't work just for atoms. We can also use this for molecules. So let's look at a fairly simple compound to start. Let's look at methane, CH4. So methane, if you're not familiar with it, this is what we call natural gas, which is what is used to heat many homes. Has the chemical formula CH4. Now, what if we had a mass, or we had 1 mole of methane? Or in other words, 6.02 times 10 to the 23rd methane molecules. So, is it as simple as going back to our periodic table and finding the mass of carbon and the mass of hydrogen and adding those together? The answer is yes. So let's go back to our periodic table. So we already have carbon highlighted here. We can see it has a mass of 12 grams for 1 mole. Up here is hydrogen, has a mass of 1 gram for 1 mole. So let's go back to methane. So that 1 carbon atom will have a mass of 12 grams per 1 mole. And the hydrogen has a mass of 1 gram per mole. However, there are 4 of them, so we're going to have to multiply this by 4. And then we add the results together. So 12 plus 4 times 1 is 16. So 1 mole of methane molecules has a mass of 16 grams. And we call this the molar mass. And we often also refer to it as the molecular weight. And our example here with methane was fairly simple, but we could do many much more complicated molecules. But before we get there, let's do another simple one. Carbon dioxide, CO2. So again, we can look at our periodic table. We find that carbon, 12 grams per mole. Oxygen, 16 grams per mole. There's 2 of them. So we multiply 16 times 2 to get 32. And then we add these together, and so the molar mass of carbon dioxide is 44 grams per mole. And we could do this for any number or any compound, regardless of how simple or complicated the chemical formula is. So let's do a more complicated one. So here is chlorophyll A. The chemical formula is C55 H72 O5 N4 Mg. Now, at first, this one is going to look a lot harder than the last two we've just done. But in reality, it's the same steps. There's just more of them. And so all we have to do is go through the same set of steps, and we will again get to our answer. So we need carbon and hydrogen again. We're also going to need nitrogen and oxygen and magnesium. So magnesium here is 24. Now it's actually slightly over 24.3. I'm just going to round here for our purposes, and in a lot of cases you can get away with that. The answer will be close enough. Nitrogen is 14 grams per mole. We'll have to multiply that times 4. Oxygen is 16 grams per mole. There's 5 of those. Hydrogen is 1 gram per mole. And there's 72 of them. And finally, our carbon is 12 grams per mole. And we have to multiply that by 55. So now we just have some arithmetic to do. There's multiplication and then add all of these together. So our 55 carbons will add up to a total of 660 plus 72 for the 72 hydrogens. The oxygens get us 80 more. 4 times 14 for the nitrogens is 56, and 24 for the magnesium. So we add all that up, and we get a total of 892 grams per mole. But in reality, we're not always going to have these nice numbers to work with. In fact, were we working in the lab, we'd very likely not be working with 1 mole of any substance. Because as you can see, once you start working with a molecule that has even a few atoms, 1 mole starts to be a pretty substantial quantity. So now let's say we had 12.7 grams of carbon dioxide. And I want you to tell me how many moles that is. Well, we just calculated the molar mass of carbon dioxide is 44 grams of carbon dioxide is equal to 1 mole of carbon dioxide. So does that become a conversion factor to allow us to go from grams of carbon dioxide to moles of carbon dioxide? The answer is yes. And so this will allow us to set up a conversion factor, just like we spent a good portion of chapter 1 doing. Because these quantities are equal, all we're doing is a unit conversion. So 12.7 grams of carbon dioxide. Now, what goes on the bottom? Do we put moles on the bottom, or do we put the molar mass on the bottom? So we have grams here. We want grams to cancel, so grams will need to go here on the bottom, moles on top, and we can calculate this out, and we get 0.29 moles of carbon dioxide. Now, what if I wanted to know how many molecules of carbon dioxide that was? Well, once I know the number of moles, that becomes a relatively straightforward calculation. So if I have 0.29 moles, and here it's carbon dioxide, but it wouldn't matter if this was carbon dioxide, water, hydrogen, chlorophyll. If I know the number of moles, I can find the number of molecules. And I can do that because we just learned that Avogadro's number, 6.02 times 10 to the 23rd, is the number of molecules in 1 mole. So now moles cancel, we multiply out here, and we find that these 0.29 moles of carbon dioxide contain 1.7 times 10 to the 23rd molecules. The last piece of this that we need is to go the other direction. So let's pick a substance and pick a number of moles. So what if we have 1.5 moles of calcium hydroxide? And I want to know the mass of it. Well, the first thing we're going to have to be able to do is convert calcium hydroxide from its name back to a chemical formula. And we can do that. Ca2+, hydroxide is -1, so we get CaOH2. Now we need to find the molar mass of calcium hydroxide. To do that, we do the same thing we've been doing. Calcium has a mass of 40. We saw a few minutes ago that oxygen is 16, hydrogen is 1. So that hydroxide there is going to be 17. But don't forget the subscript here, which applies to the entire hydroxide, but not the calcium. So this 17 for the O and the H gets multiplied by 2. We add the results together and we get the molar mass of calcium hydroxide is 74 grams per 1 mole. Now, we take our 1.5 moles and we're going to multiply, convert back to grams. So when we went from grams to moles, we put grams on the bottom. Now we're going from moles to grams, so we have to do the opposite. Moles go on the bottom, 74 grams go on top, and if we calculate this out, we get 111 grams. But recall, our starting number has only 2 significant figures. That means our ending number also needs to have 2 significant figures. So our 111 grams here will get rounded to 2 significant figures, or 110 grams. So from here, you should now go to in-class exercise number 6, working on balancing, in-class exercise number 5. And on that sheet, you'll be doing a number of calculations where you're looking at grams to moles as well as moles to grams. You should work on those and then come back to the next section of lecture.